Okay, chapter 5 is electric currents. The first part of this is about electric potential, potential difference, current, resistance. The second portion, 5.2, is about electric circuits. So, a lot of definitions in the first part, which you probably want to go through. 5.1.1 is the definition of electric potential difference. 5.2.1 is defining electromotive force. I usually like to define both of those at the same time. So basically, when let's say we have a circuit. This is the symbol for a cell. Multiple cells would be a battery. So this is the symbol for a resistor. So the student should be basically familiar with most of the symbols from the IGCSE. So, but yeah, you can obviously go through it again if they're not confident with this. The shorter end here is usually the negative terminal, and the longer end is the positive terminal. Okay, so what happens in a circuit? You have charges flowing from one end. They complete the circuit and they go back to the other end of the battery. So, in actual life, we know that electrons are traveling in a circuit. They travel from the negative terminal to the positive terminal. So, this is the direction of electrons flowing. Okay, but conventional current, as the student should be familiar, is always in the opposite direction. Conventional current moves from the positive terminal to the negative terminal. Okay, so this is the direction of conventional current. Okay, so it's like this due to historical reasons, and they should accept this as an axiom. So now, for simplicity's sake, let's assume that there are positive charges moving in this circuit. So we know for a fact that positive charges do not move in the circuit. It's the negatively charged electrons, but for simplicity's sake, let's assume that there are positive charges moving. So these positive charges, when they're at the negative terminal, each of them will gain energy. The battery will supply energy to these charges, and they will gain energy. Okay? Gaining energy or in a circuit is pretty much like taking the examples that I give are usually like those toy cars being put up on a height and then being dropped on a circuit. And as these toy cars drop along the circuit, they will lose energy. You can also give the example of flowing water, and there's a water wheel. Water wheel will bring the water up to the top of a slide. So, and basically bringing it up is giving it gravitational potential energy. In this case, the battery is providing the charges with electric potential energy. So, the battery will provide energy to the charges here, and then the charges will flow across the circuit. Okay, every time they come across a resistance, what will happen is they will lose energy. Okay, so this is the energy level of the charges. Okay, so when they come across a resistor, they lose energy. Their electrical energy is converted to other forms of energy. So for example, if this is a bulb, the electrical energy is converted to light and heat. If this is a fan, it's converted to mechanical energy, etc. So at this point, the charges have lost their energy and they come back here to the beginning of the circuit. Then again, these charges will gain energy in the battery and so on and so forth. Now over here, the gain in energy. Okay, so the gain in energy per unit charge. Okay, so the amount of energy in joules gain per unit charge in the battery, or the amount of energy supplied by the battery per unit charge is called the EMF, electromotive force. Notice, even though it says force, it is not a force. Electromotive force is measured in volts, just like potential difference, and it's not a force, so you must make that clear. And over here there is energy lost or dissipated. Okay, so technically it is not lost, the electrical energy is converted to other forms of energy. So the energy lost or dissipated per unit charge is called the potential difference. Okay, so the difference in potential. Over here the charges were at a higher potential when their energy was converted to other forms. Now over here they are at a lower potential. So this difference in the potential is called the potential difference. So the energy lost per unit charge. Charge is measured in coulombs. Okay, energy here is measured in joules. Potential difference will be measured in volts. EMF here measured in volts, charge measured in coulombs, energy measured in joules. Alright? So for example, once they understand this, this will define, this will take care of 5.1.1 and 5.2.1. Okay? Now, let's say that we have a charge, or let's say there is a positive charge, okay, one positive charge, 1 unit of charge, and it's moving from a potential of positive 2 volts to negative 0 volts. Okay, so the potential difference across this is 2 volts. Okay, now, so due to this potential difference, this charge is going to be accelerated. It will gain energy. This charge is going to lose electrical energy, which will be converted to other forms of energy. Right? So the electrical energy lost from this point to this point is the loss in potential energy of this charge. So how do we calculate that? We know that the potential difference is defined as the energy lost. Let me see what the symbol is. So over here they write it as W, which also means the work being done by the charge, right? So this charge, in moving from here to here, is converting its potential energy to other forms of energy, and hence doing work. So the work done divided by the charge, which means the work done per unit charge is defined as the potential difference. Right? Okay. So now let's say this was one unit of charge, which would be 1 electron charge. Okay. That is, let's just put it in coulombs. 1.6 times 10 to the power minus 19 coulombs. Right? And this is the potential difference of 2 volts. Now I want to know what's the potential energy which has been lost between this point and that point. What's the potential energy difference? So how much potential energy has the charge lost? So I just have to put in the values. 2 volts here equals W, or potential energy lost divided by the charge, which would be 1.6 times 10 to the power minus 19 coulombs. Okay, so therefore the potential energy lost will be equal to 1.6 times 10 to the power minus 19 times 2 joules. Okay, so now rather than, when we are talking about point or individual charges, right, 1 electron, a bunch of electrons, like 10 electrons, in a very microscopic level, it becomes cumbersome to deal with such a large number all the time. So therefore they have defined another unit for measuring energy. Now, remember that this is a unit of energy. 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. 1 electron volt is the amount of energy lost or gained by a single electron or a single electron charge when it moves through a potential difference of 1 volt. Right? So in this case, this will be equal to 2 electron volts. Right? So it makes calculation much easier and less cumbersome. We don't have to include the electron charge all the time. So another example, for example, if we had let's say a potential difference of 50 volts and we had moving from 0 volts to positive 50 volts, and we have how many? We have 3 electrons. Okay? So how much potential energy would be lost by them in getting accelerated from here to here? So how much potential energy is being converted to other forms of energy? Right? So, or what is the kinetic energy gained by these electrons in moving from here to here? That would be simply 50 volts multiplied with 3 electron charges, that's equal to 150 electron volts. Okay? This is a unit of energy. Cool? So that is the definition of an electron volt. Now the next portion here is basically solving problems using electric potential difference. That's okay. 5.1.5. Define electric current. Now electric current, okay, is of course practically defined as the amount of charge, okay, traveling per unit time. So the amount of charge traveling in a circuit per unit time is the current. However, this is not a formal definition of current. The formal definition of current, or an ampere for example, has to do with the force per unit length between two parallel current carrying conductors. So when we go to the topic of magnetism, we will know that when there are two current carrying conductors, okay, right. So when there are two current carrying conductors, there will be a force of attraction or repulsion on them, depending on what's the direction of the current, whether they are in the same direction or in the opposite directions. Okay, so in this case, for example, this current carrying conductor is going to produce a B field which is going into the page at this point. Okay, so if we use our right hand rule, we will know that there is a force acting outwards on this conductor. Okay, so but that's not the important thing, and that's not the detail that you want to go into in this chapter. The force per unit length is defined as force is given by BIL. Okay, and the B is dependent on, okay, again force per unit length would be BI. B is dependent on a few variables, which is the permittivity of free space, the current on each of these, the current on the conductor that is producing this B field, and also the distance between these two current carrying conductors. So now the definition of 1 ampere then is the force per unit length produced on two current carrying conductors of infinite length, which are 1 meter apart and have a negligible radius. You don't need to go into the exact details of this. You can get this information online. It's not in their curriculum, but it is sufficient for them to know that the definition has to do with the force per unit length between